hear you. Can you hear us?
Yeah, because somebody talk now.
How about now? Can you hear us?
Yeah, I can hear you now. Okay, can you also hear me, right?
Yes.
Thank you so much for confirming that. Yeah. Good morning, everyone. I want to welcome you to another beautiful week. Before I get started today, I want to make this announcement for those of you who have not heard about information that the assignment one has already been uploaded. Like I said, assignment will be uploaded every Sunday and will be due the following Sunday. So please make sure you check information on Canvas from time to time. Okay, so the materials for this week have already been uploaded. Okay, yeah, go ahead. Yeah, it's through online. If you look at the instruction, through file upload. You mean whether screenshot, right? Yeah, actually, kind of flexible. If you can write legibly, like write clearly, you can just take the picture. But when you take the picture, save with PDF. Does that make sense? You can write, you can type, but make sure you, with for those of you that will be writing, let it be clear because it's my TA that will grade that. So it's only when there's an issue that I'm actually going to call, look at what she has graded. Does that make sense? But make sure you save with PDF. Okay, that's a good question. Yeah, the materials for this week have already been uploaded. And of course, we're starting with the first material of the week. Like we got a lot to cover this week. So I'm basically going to start with probability model. Okay. Now, in the probability model, I'm going to cover probability spaces, probability measures, and probability model itself, or probably with some exercise. I think I introduced you to this last week. It's one of the materials listed for last week that I actually, bring forward for today. Okay, so that is the outline. I'm actually, of course, I told you the other time, we live in a stochastic environment, we live in a probability space. And of course, for us to be able to understand our political environment, our economic environment, our socio-economic environment, psychological environment, and so on like that, we need to be able to understand some basic probabilistic terminologies. And that's why you are here learning this. Okay, so the very first thing you can see on my slide is what we call random experiment. Okay, when we talk about random experiment, we're talking about when an experiment is performed repeatedly or under similar condition, and that generates more than one outcome. Otherwise, if you only have one outcome, okay, when you repeat experiments infinitely, of course, that will be deterministic and we don't need to be worried, okay? But why do we need to be worried in this type of the world? Because of the fact that when you perform experiment, there are more than one possible outcome. Now, that's what we mean. And we all perform experiments every day. Okay, now, but let me tell you this. The experiment we're talking about can actually be described or modeled by a probability space. When I talk about probability space, I'm actually talking about triplets. You know, triplet, like number one, you talk about sample space, which I call omega. The sample space is going to tell us, you know, the collection of possible outcome. Then we're also going to have a calling F. The calling F is actually represent all events. You know, all event does not necessarily translate to all outcome. I'm going to say that again. All events does not translate to all outcome. Outcome is different from events. Does that make sense to you now? Please, I needed to take note of that. Now, the calling F that we're talking about is talking about, you know, we're talking about our event, which I said, and that because we're talking about our event, that is what actually make it to be bigger than the sample space. Does that make sense now? And we also have what we call a probability measure. Let me tell you this. When you perform experiment, you have a sample space. From the sample space, you can get calling F. The calling F is the power of a set. When a sample space has two possible outcomes, of course, the calling F is going to be 4, which is 2 raised to power 2. I walk you through this the other time, and that was what make the set, the number of sets in the calling F, in the power of a set, to be bigger than the sample space itself. And let me tell you this. We said the calling F actually means some events. Every event, we have a probability of occurrence. I'm going to say that again. Every event has a probability of occurrence. That's what we call the probability measure. You get what I mean now? When you have an event, okay, there will be probability associated with that event. Okay, now this is an example of a sample space I just talked about. When you have a die and you toss a die once, okay, we got 6 possibility, okay. But let me tell you something. There is only condition under which the power of a set is defined when the omega is finite. Because if you don't know the numbers of elements in the omega, then it means your power of a set will be 2 raised to power what? Infinity. Okay, of course, that is indeterminate. Okay, and that's why here we are interested in the number of events that can actually be counted. So when I have a sample space omega 1, 2, 3, 4, 5, 6, of course that can never be a calling F. The calling F here will be 2 raised to power 6, and that will be a lot. Okay. Now another example I'm giving is where you have a fiat coin. A fiat coin is stored 3 times. Okay. Of course, when the fair coin is stored 3 times, you're actually going to have that as a possible, numbers of, outcome that you can have. Like I said, possible number of outcome, it is not the same as possible numbers of events. There's a difference between an outcome and an event. Please take note of that. As students trying to, confuse the two words, they are not the same. Go ahead.
The difference be like head, tail, head, but then like the outcome be you wanted 2 heads?
Oh, that's it. That's a very good question. You know, when you said in a coin, like when you have head and tail, right? Okay. Now the possibility is head and tail, like when you toss it once. But when you want to talk about outcome, the outcome is in your mind. It's in my mind. Maybe my outcome is uh, what is the possibility of having head? Another person may be, what is the probability of having tail? Another person could be, what is the probability of having the two together, stuff like that. That becomes an event. And that was why, when you take a look at, that of a die, where you have 1, 2, 3, 4, 5, 6, somebody's event may be event of number less than 4. Somebody may be event of number less than 6. Somebody may be, maybe his own event may be even numbers, odd numbers. There's so many of that. And that was why we said, event, the possible event we're going to have would be more than the outcome in the sample space. Does that make sense to you now? That's a very good question. Have I answered your question? Good job. Okay, now, if you take a look at what I have now, okay, I just displayed that to you. That's a sample space, which is a collection of possible outcome, but not the collection of possible events. So if I want to talk about collection of possible events, then I'm actually going to be looking for a calling F, which is going to be the power of a set. Does that make sense now? Okay. Now, this is this is a case of when a coin is tossed once. You can say the sample space omega is head, comma, tail. Okay, these are possible outcome. Those are not possible events. The possible event, like if I'm now looking at the calling F, you can say the number of elements in the calling F is even more than the sample space. Okay, that is what you can see. But take a look at this. When I have a calling F now, if I now want to talk about a probability measure, the probability measure is not going to be a function that will map the element in the calling F, okay, into a range of 0, 1. Well, when I say it's the range of 0, 1, for instance, when you take a look at the calling F, where I got empty, head, tail, if I want to find what is the probability of empty, the probability of empty in the calling F, what is the probability of head in the calling F, what is the probability of T in the calling F, what is the probability of HT in the calling F. With that, I'm actually referring to probability measure. And that was why you can see, I said the probability measure is a function that map events in where? Event in the calling F. Event in the calling F to a real number in the range of 0, 1. Go ahead.
So like in that example, if the outcome we were looking for was whether like two coin flips, would it just be like head, tails?
Never.
No.
Never. It's going to be, you're going to use a tree diagram. The sample space changes when the numbers of triad changes. This is a situation where we had a formula for that, okay? The formula, since you have two sides in the die, right? It is 2 raised to power n, where n, if I toss the coin once, okay, the sample space is going to be just this guy, 1, 2. So which is going to be 2 raised to power 1, 2. If you toss it twice, okay, you can make use of the tree diagram, okay, because now we take use of that. So what are you going to have? Head, okay, head, tail, head, tail, 1, 2, 3, 4. So 2 raised to power 2. That's 4. Does that make sense to you now? So when the numbers of triad increases, you expect more outcome in the sample space. That's a good question. Okay, now when we take a look at the axioms now, when I say event A depends on what the researcher has in mind. Does that make sense now? Okay, so, but the event A, the probability of that, when I say event A may be empty, A may be H, based on what I'm projecting now. And A may be event of having tail. A may be event of having the other one. And that was why the axioms that you see actually revolve around, the probability of A. So we say, okay, you know what? The probability of A is greater or equal to 0. Why do we say equal to 0? Probability of A, which means, don't forget, the range of probability will go from 0 to 1. So which means the probability cannot be negative. And when you take a look at the sample space, the probability of the sample space is always equal to 1. Why? Because it's a sure event. Okay, any of that will happen. Does that make sense now? So I need to take note of that. The probability of sample space, the probability of omega is always equal to 1. Then we'll take a look at the axiom 3. A1, A2. Why do we have A1, A2, A3, A4? Because we got a lot of events in the calling F. We're not talking about the sample space right now. We're talking about calling F. The calling F is bigger than the sample space. So, and that was why we can have A1, A2. I told you the other time. Maybe if you're talking about the issue of a die, A1 may be the event of odd numbers. A2 may be the event of even numbers. A3 may be the event of number less than 4. If and so on like that. That's why you have A1, A2, A3, and so on like that. But let me tell you, they are disjoint events. What do I mean by disjoint? They are mutually exclusive. Mutually exclusive means the occurrence of one, okay, actually prevents the other. The two of them cannot occur at the same time. That's exactly what we mean by disjoint. Does that make sense to you now? Now, it is only when you got a disjoint that this law now holds. If you take a look at the law, the probability of A1 union A2 union A3 and so on like that, that will automatically be equal to the sum of the probability. So which means the union law, okay, translates into addition rule in probability. The union law. But provided the event you are seeking the union are disjoint. Okay? Yeah, go ahead.
I guess I'm kind of just confused how you got head tails with the head.
Oh, how do I get the airtail?
Yeah.
No, the coordinate is the power of a set. The power of a set that you did on the live stream when you have H and T, you first consider when it stand alone H, when you have a T, and when you have the combination of the two and the empty.
Wait, how can you have the combination?
No, that is it's just the combination of it's not as if you can have the combination of the two in real life, but we're trying to talk about the way it appears in the set, the way they can stand. It said that I have two, I have H, I have T. The possibility of standing now is what we're talking about. Like we can have H that stand alone, we can have a T that stand alone, and we can also have them standing together. So the H and T that you see inside the coordinate is the sample space. I'm going to say that again. The H and T is repeated, right? In the coordinate, that is the sample space. And that was why I said the other time, the sample space is inside the coordinate. It's not as if it happened in reality. I understand where you're going. Does that make sense now? Go ahead.
And then the probability, it's infinite because we can just make up different probabilities like in our minds or whatever.
Yeah, but you know what's going to happen? We said the other time that the probability measure go from 0 to 1, right? What the H and T that you see will definitely have a probability of 1 because the probability of a sure event is 1. What about the NT? The NT, we have the probability of 0. Then the one in the middle now is the probability that makes sense in real life. Because it's either you see head or you see tail when you toss a coin once. So which means the empty one and the one that guy said about H and T, they are extreme probability, where you say probability can be 0 and 1. Those are extreme values. I'm happy today you guys have a very sensible questions. Okay, let's keep going. Okay, now this is where we're going. At this point, I need you to pay more attention because we're going to be dealing with some kind of derivation, going to be going mathematical. Those of you online, can somebody still confirm if you can still hear me clearly? Please, if I wanted to confirm, I wanted to confirm by talking. Thank you so much. Okay,
Yes.
thank you for confirming that. Now, we are now in probability of events. Now, whatever we're going to be doing right now, we centered on probability associated with events. Now, I wanted to, and that was why here, using this theory, the assumptions that we talked about before, I'm basically going to walk you through some preposition that we basically call law. Okay, now let's take a look at the law of proposition number 1. What does it mean? The proposition number 1 is trying to say, don't forget, the A here is not an outcome, it's an event. Does that make sense? Please see A as an event. Where can you have event? Is it in the sample space or in the coordinate? In the coordinate. What you have in the sample space is event. Oh, sorry. What you have in the sample space is outcome. While what you have in the coordinate is an event. Okay, now the probability of A complement equal 1 minus probability of A. How do I actually arrive at that? When I have a when you take a look at you have a Venn diagram, okay, and you are considering, let's say there are only two events that we have in the in the sample space. We have A and A complement. Okay, so that A and A complement means if it is, I'm focusing, maybe A may be egg, and maybe A complement may be tail, something other than egg. Now, because of the fact that A and A complement are disjunct, of course, A and not A, they have to be disjoint. There shouldn't be any kind of connection between them. Now, let me tell you this. When I take the union of disjoint, please take note of this. When I take the union of two events that are disjoint, okay? Now, when I take the union, which is A union A complement, that will automatically be equal to sample space. I'm going to say that again. If there are two events that we can only have, there's no any other event, A and A complement. When I take the union of that, the union of A and A complement will actually be omega. And if it is omega, since A and A complement are disjoint, they are mutually exclusive, then if I introduce probability to both sides, what is the probability of omega? It's 1. I showed you the other time. Now, what is the probability of A union A complement? The probability of A union A complement, if you want to go by this guy, if you want to go by the last thing, is adding the probability together. The probability of A union A complement will now be probability of A plus the probability of A complement. So the probability of A plus probability of A complement will be equal to 1. Don't forget, 1 is the probability of the sample space. Then solve the equation, whatever you're looking for. Since you know the probability of A plus probability of A complement equal to 1, then if I want to find the probability of A complement, it's just going to be 1 minus the other one. Any question? Now, I've just proved the proposition number 1. Any question? On the way I proved that, I use the union of two disjoint sets. When they are disjoint, and you take the probability associated with the union of the disjoint set, it's automatically going to be the addition of the two probabilities. And that will be equal to the probability of the sample space. The probability of the sample space equal to 1, then the proposition number 1, now you verify that. Now I'm going to go into proposition number 2. You know, if you look at proposition 2, A belongs to B, okay, we're told A belongs to B, okay, and the probability of A, the probability of A less or equal to probability of B. You know, you can be asked to prove stuff like this. I want you to take a look at that. A belongs to B. If I want to prove something like this, you know what I'm going to do? What I'm actually going to do is I can go through a Venn diagram. Okay? I can actually go to a Venn diagram where I can just do this. This is A, this is B. Okay? Now, if A belongs to B, okay, you know what I mean, what I actually mean if I have this. Let's see. If A union B, okay, is actually equal to B, then it definitely means A is inside B for you to be able to, you know, to have that in a way. And if you take a look at what I actually presented, I said B equal, that was why I said B equal to A union B. Okay, B equal to A union B, okay, if A belongs to B. So in a way, if I want to rewrite that in order not to cause confusion, I can do what I do the other time, where I actually just write 1, okay, and put this guy here, okay. You see, when I was drawing the other time, you can look at this now. if A belongs to B. Any question? Take a look at it. This is another beautiful way to represent that. Here, you can actually see A is inside B. Okay? And if A is inside B, if I do the union of the two, I'm still talking about B. You see that now? This is a very good representation of that. Now, if this is a very good representation of that, now I now said A union B, okay, A union B, I said equal to omega, okay, intersection A union B. Let's see whether it makes sense, okay. What is the intersection, what is common between the omega, which is going to be the whole thing. You know, when you take a look at this guy and outside, that is the omega, right? Okay, and outside that is the omega, right? Okay, so now the intersection between this guy and this guy is still this guy. It's still a union B. That's why I said it should make use of Venn diagram. Of course, when you make use of Venn diagram, everything is going to look so great. Okay, now that is what I actually have. Okay, up to that. Now the question now, I want to rewrite omega as something. I can rewrite this omega as what we just did. What did I call omega? What I just did? A union A complement. That's omega, right? A union A complement. So this guy is going to be A union A complement. Okay, this A union B. So this guy now is actually the omega. That's omega. Okay, A union, when I say A, I'm talking about this is A. And A complement is everything. Everything other than this. Okay? Outside. Outside is going to include this guy. And outside. That's going to be A complement. And that is basically that. Look at that. Oh my God. Where are we now? Take a look at where we are now. You can see we're there now. A union, A complement, intersection, A union B. I will advise, please make sure you make use of a parenthesis in order not to cause a confusion. So you can use a parenthesis here. Okay, it's another parenthesis. You can see that, right? Okay, now when you take a look at what we have now, you can now use the idea of a distributive law. Okay, like a way of factorizing. Okay, if I have something written A union, A complement, intersection, A union B, how can I can write it as A union. So I'm actually going to rewrite that. Okay, so that's why you can say A union, okay, A complement, intersection B. Okay, what am I trying to say? Okay, this multiplied by this, you're going to have that, and that by that, you are having that. So which means this guy is the same thing as what you have here. Okay, so you can look at that. And don't forget, what was equal to all of that, okay, don't forget, we said from time, B equal to that, B equal to this, B equal to this, so B equal to that. Okay, now, if you take a look at this, A union A complement intersection B, that is exactly what you can see. Now, we want to focus on A. We want to focus on this event. We also want to focus on this particular event. Now, when you take a look at, the other time, this is what we draw. Okay, this is B, and this is A, right? Don't forget, A belongs to B, right? Now, when you take a look at A, this is the whole A, right? Okay, now you want to look at A complement intersection B. Okay, the A complement intersection B means the element does not belong to A, but the element belongs to B. Hello? Element does not belong to A, but the element belongs to B. I'm talking about this side. You see that? This guy means B minus A. For those of you who have done the symmetric, the relative difference. Now, this is A. This side is this side. What happened to them? They had disjoint. If they are disjoint, I can apply additional rule of probability. Okay, now, and that was why the probability, when I introduce a probability to this guy now, the probability of B will be probability of A plus, don't forget, when they are disjoint, and I'm looking at the union between them and they are disjoint, the addition rule in probability can be imposed. So right now, I'm actually going to have this guy. Oh my God, take a look at this now. You're basically going to see that this guy is greater than this guy because this guy will be greater than or equal to 0. You've already proved that. And that shows the probability of A is less. You know, another way to rewrite this is to write the probability of B greater or equal to that. They made the same thing. And right now, this guy is greater than this guy because this guy is non-negative. This guy exists. The only condition that they're going to be equal is when this is equal to 0. It's not possible based on what you see. And that was why we can say it may be possible. That was why we say this less or equal. We've already included that. Provided if this is 0, it's going to be equal. If this is greater than 0, it's going to be equal.
So if it was 0, wouldn't it be the exact same set?
If it is what?
If it was equal to 0, wouldn't it?
They will be the same. That was why you had this. Do you see less or equal? They've considered that the least it can be is when they are equal. And equal means when this guy equal to 0. But if it is not, this guy, and of course, this cannot be negative, right? Okay, say that it is 0 or greater than 0. Okay, that's the preposition 2. Now the preposition 3 now. I told you the other time when I was talking about calling F, the probability of MT is 0. If let me take you back. You know, the probability of MT is 0. The probability of H, T together is 1. Because the H comma T is the sample space, and the probability of H, the probability of T, is a realistic probability. Because when you throw a coin once, it's either you see tail or head, provided the coin is fair. Okay. Now, for proposition number 3, we can also prove that. But how are you going to prove that? Okay. If you want to prove the proposition number 3 now, okay, where we say the probability of an empty space, okay, the probability of an empty space is equal to 0. Now, if you look at my provision, we need to take a look at the omega itself and the empty set. Now the question we need to first ask ourselves, is omega an empty disjoint? Yes. This is another confirmation that empty is not in the omega. Somebody asked a question the other time, whether there is empty, even though empty can be. I told you, anytime the only area that we want to consider an empty is when you're talking about the calling head. Okay? We believe empty is not in the omega. Empty is not in the sample space. Therefore, the two of them are disjoint. And if the two of them are disjoint, you know, this guy is also going to give this guy the union of the two. Now, we have now established the fact that this and this are disjoint. Then I can do the probability of that plus the probability of that equal the probability of that. And this guy is a sure event. 1, that's another 1. Okay, plus this. What happened? That equal 1 minus 1 is equal to 0. Take a look at that. Okay, that was how we are able to establish the fact that the probability of an empty set equal to 0. Now we want to go to preposition number 4. I need you to pay attention to the way. I'm not going to go by the way it is done here. I'm going to show you my way. If you really quickly want Let me see. I think, yeah, we're going to finish that on time. Okay, now this is what happened. I needed to pay attention. Can somebody online confirm? I think you guys have been seeing what I wrote on the board, right? So if you're online?
Yes. Yes.
Okay, good. Thank you for confirming that. Okay, now we actually have two major events, and one does not belong to the other. The one we just finished right now, an event belonging to another event. It's just like School of Statistics belonging to College of Liberal Arts. Of course, we don't expect School of Statistics to be bigger than the College of Liberal Arts because the School of Statistics is inside the College of Liberal Arts. But right now, we're not interested in that. We're interested in two major events, and they don't belong to each other. Okay? Now, I'm talking about, we are on position number 4. Okay? We got, using the Venn diagram, we got this. Okay? And there's omega. Now, A, when I say all A, everything about A, everything A is this guy. All B, everything about B is this guy. Okay, I need you to pay attention now. You know what we want to prove, right? We basically want to prove that the probability of A union B equal to the probability of A plus probability of B minus the probability of A intersection B. You know what we call that? We actually call that non-mutually exclusive. Non-mutually exclusive. Before I go ahead to prove this, I'll tell you the meaning in real life. I order from 2 different restaurants. I order from Wendy's, and I order from maybe McDonald's. Now, and I want to figure out what is the probability that the order will come on time. There are 3 possibilities. It's either this guy arrived my house on time, or this guy arrived on time, or the 2 of them arrive on time. That's what I want to prove. The probability of A is, it arrived on time. I just see a DoorDash man knocking on my door, and it's coming from McDonald's, or the one from Wendy's arrived on time, or I just look at my door and see two of them arriving on time. That's a possibility. And we're actually going to call this inclusion and exclusion law. Why do we call it inclusion and exclusion? Inclusion is why we're adding them. Exclusion is when we are subtracting what is common to them. Now, I want to prove that now. And I need you to focus on the board. This guy is A intersection B. That is where they arrive on time. The 2 of them came together. This guy is A intersection B complement. The meaning of just this side is A only. A only does not include B. This guy is A complement intersection B, which is what? B only. Does that make sense to you now? Please, if you don't understand, ask question. Now, if you take a look at what I have, what is A union B? Okay, if I want to talk about A union B, okay, now this time around I'm going to be talking about the cardinality. These are just events. Okay, what is the cardinality? Before I can actually come to probability, I first need to talk about cardinality. Now, what is the cardinality of this guy? It's just going to be adding, A union B is adding all of them. Okay, it's going to be this guy now plus this guy. Okay, plus this guy. Any question on why I add them up? Because we are talking about A union B, addition of all of them. Now, I'm actually going to call this guy equation 1. Okay? Now, I want to focus on what is about the cardinality of A. A is this guy. Okay? We're going to have this plus that. I'm going to call that equation 2. What about the cardinality of B? The cardinality of B is this guy plus this guy. I'm going to call that equation 3. Take a look at that. Okay. Now, you know what I'm going to do now? From equation 2, I want to obtain this guy. I want to solve for that guy. And from equation 3, I want to solve for that guy. So that when I solve for this guy in equation 2, and I solve for this guy in equation 3, then I'm going to plug them into equation 1. Then I'm just going to simplify. Okay, now, if that is what I have right now, okay, I want to go up. I want to write up here. Now, take a look at from 2. Now, what is this guy? This guy, okay, it's going to be this guy minus this guy. I'm going to call that equation 4. Okay, from 3 right now, okay, this guy, okay, equal this guy minus this guy. I'm going to call that equation 5. Any question? Just solving for this and that. Now what I'm going to do now, I'm actually going to plug in equation 4 and 5 into equation 1. Plug in equation 4 and 5 into equation 1. Okay. Now, if I'm going to do that, this is equation 1. I'm actually going to have this equal, what is this guy? Okay, is this minus this. Okay, I just get that one out. Then plus this guy, plus now this guy, which is this guy. Look at that. I just see that now, right? Okay, this. Cancel this. What do I have? The cardinality of this guy equal this plus this minus that. In terms of cardinality, this is what I have. If I want to find the probability associated with that, what is the probability of A union that? Okay, it's going to be the cardinality of this divided by the cardinality of the sample space plus the cardinality of this divided by the cardinality of the sample space minus the cardinality of this divided by the cardinality of the sample space. So when I have the cardinality of an event divided by the cardinality of the sample space, that becomes the probability of that. Okay, so what I'm trying to talk about now, it's going to be okay. So if I now want to rewrite all of that now, it's going to be the probability of A plus the probability of B minus the probability of the intersection, and that is the end of the proof. Take a look at that. Any question? That's how that is proved. I can ask you to prove for 3 events. Let's watch out. I'm going to show you that. I just finished all of that. Show you that. I just finished all of that, right? That's another way of doing that. Then this is for the 3 events. Watch out for that. I can ask you to prove for 3 events. Practice that. The probability of A union B union C. Prove that it's all equal to that. Equal to the probability of A plus probability of B plus probability of C minus the probability of the intersection A and B, A and C, B and C plus the probability of A intersection B intersection C. If I now want to generalize that, this is the generalization now. You know what that generalization is talking about? I'm actually adding the single event A, B, C. That's why you say summation the probability of AI. Okay, and you can see if I want to represent union, if I have a lot of events, I can just write U AI. You remember we did that in the last class. Okay, so this is a general principle, the general formula. We're talking about an event, okay, and we call that inclusion exclusion principle. Okay, that's what we call it. I put some exercises here. That's going to be the end of my lecture today. Any question? Right.
When we're doing our own proofs, can we use those propositions that we were just showed as facts, or should we prove them every time we're doing a proof?
You can use whatever. You can use provided you prove and you're able to demonstrate that you've already proved that. You get what I mean? So you can use what I show in my slide. You can use maybe you read a textbook. We have a textbook for this course, right? Okay, so you can do that. Does that make sense? Yeah, you can do that. You can do whatever to show you proof.
Would we
But-
copy that on the homework?
Or whether you can copy that on your
Or like
homework.
the proposition you showed, would we copy that on the homework and use it, or can we just say that it works?
Yeah, provided if I ask question about that in the homework, of course you can just write you can just write for the homework, or you write this, or whichever way you think about it. You get what I mean? So, but in the exam, of course, the exam you are not going to be allowed to open your book, even though I'm going to allow sheet. I'm still going to make an announcement about how. But if I ask a question, it's open. You can copy from anywhere. You understand what I mean? But provided I know how to catch students who actually, I know some instructor put some solution online to some questions, which I've already seen. But I need you to demonstrate your own understanding. You can see that when I provided this, I also show you my own way. If you take a look at this my way and this way, this is looking complicated either way, the one I'm showing on the slide. But if you understand it, you can present it your own way, but you are not going to be penalized. Like if you get that from my book, you know what I mean? As in from the lecture, no, there's no problem. Okay, but in exam, I just wanted